To find the volume of a solid of revolution, we're going to first use the disk method. So I wrote out, if you're rotating around a horizontal axis, you're going to use the integral from a to b pi r squared dx. If you're rotating about a vertical axis, it's the integral, and then you have your limits, pi r squared, and then it's going to be dy. This example says find the volume of the solid obtained by rotating the region bounded by the given curves about the specified axis. So for part A, y equals the square root of x minus 1, x equals 2, x equals 5, y equals 0, about the x-axis. So I have the region bounded by the given curves drawn right here. You have your square root graph, it's been shifted to the right 1, and then you have x equals 2, x equals 5, and then y equals 0. So basically you want to look to see where would that shaded region be, and you want to think about rotating this region around the x-axis. Obviously a computer-generated diagram would work a little better, but I'm going to attempt to rotate this around the x-axis so you can see what's going on. So this point right now is up 2 units, so it's going to rotate all the way down 2 units. So kind of picture this point right here that's over 5 up 2, rotating down all the way to over 5 down 2, and then it spins like this. You're going to do the same thing with this point right here. So if you can kind of picture this, it kind of looks like a lampshade on its side. So what's happening in the disk method is we're taking cross sections. So I just arbitrarily drew the disk right here. There's an infinite number of disks that you could draw from 2 to 5, that if you added up their volumes, it would create the total volume. R starts on the axis of rotation. You draw it perpendicular to that axis of rotation, and you draw it towards the shaded region. And you can see that R in this case is just the height of this curve, square root of x minus 1. A couple of things for this problem. We're rotating around a horizontal line, so it makes this a dx problem. Then you look at the original shaded region, and you look to see in the x direction where this region exists from. So the shaded region exists from 2 to 5, and that's why my limits are 2 to 5. And then your formula for disk method is pi and then r squared. And we identified r over here. R is the height of the curve, which is the square root of x minus 1. If the problem was just asking us to set up only, this would be our answer. But I'm going to continue working this out. The square root and the square cancel. I pulled the pi to the front. It's a constant, so you can just move it to the front. And now we're ready to integrate. Finally, plug in 5 and subtract plugging in 2. So you get 15 pi over 2. This next problem we have y equals x cubed, y equals 27, x equals 0, about the y-axis. So here, since we're rotating around the y-axis, which is a vertical line, this is going to be a dy problem. So I'm not going to draw actually rotating it, but I am going to draw the r value. So you always draw the r perpendicular to the axis of rotation, and you draw it towards the shaded region. So I arbitrarily chose to draw it right there. I could have drawn it lower where it would have been smaller, or I could have drawn it higher and it would have been a little bit longer. So like I mentioned before, this is a dy problem. So as far as your limits go, look at the shaded region, and in the y direction you go from 0 all the way to 27. Then your formula is pi r squared for the disk method, and then go ahead and make sure to write dy at the end. Now we have r. To find r, again, r is related to the curve. So I wrote down y equals x cubed for the curve. But the thing about this is r is how far you're going out horizontally. So I could put an x right here, because r starts on the y-axis and it goes a generic distance out horizontally, hence the x. But this is a dy problem. So we don't want to leave the x here. Instead, we want to take this equation and we want to solve for x in terms of y. You end up getting that x equals y to the 1/3, and that's the expression we're going to plug in right here for x. And here's our setup. We have pi, the integral from 0 to 27, and then we have y to the 1/3, quantity squared dy. First, I rewrote it as y to the 2/3, and now we're ready to integrate. I'm actually going to pull this 3/5 to the front, and now we're going to plug in 27 minus plugging in 0. Okay, we're almost done. We just want to simplify this. Take care of the root first. The cube root of 27 is 3. And then you have 3 to the 5th, so you get 729 over 5 pi.